Okay, welcome folks. So today, lecture 13, what we're going to be doing is talking about friction and drag. Gonna spend most of our time on friction, gonna go into drag just a little bit. They're somewhat related. But like I said, most of the analysis we're gonna do and most of the problems that you'll have in turn to do are gonna involve friction. Okay, so that is where we're gonna get going. Now, this first discussion of friction is easier if you can see a demonstration of it, but I just want you to imagine a situation for a moment. And you can go do this with like a book or a small box, like a tissue box or something in your house. Just, you got a wall here, and then you got a box there. And the idea, and this is probably a well-known phenomenon, you know that if you push with some applied force against the box, you can get it to stick. Well, not stick, but like you can get it to not fall. Like pinching it between your finger and the wall is basically a way to hold it in place. Um, and the question is why? Like if we start looking at the free body diagrams of this stuff, why does this actually work? So let's just take a look at the FBD of this situation. Now, I do encourage you to try and to see if you can get there are four relevant forces on this box. I encourage you to see if you can get them all. So pause that, see if you can get them all. But the first one is going to be gravity. So all these things have weights. That means they will have a force of gravity on them, and that will just be equal to mg. Now the next one obviously is going to be the applied force, and absent some sort of scale, we don't know what that applied force is going to be. They got like a bathroom scale is what we need in order to figure out the force of the press. So we don't know what that is going to be, but we do know that because the wall is a solid object and it's not going to allow the scale to accelerate into the wall. Basically, what we're going to have is we're going to have a corresponding normal force pushing back out against it, and those two forces will be equal. Okay, so those will be the two forces. Now, as this free body diagram currently sits, this thing would fall, like it would accelerate downward due to gravity. Those horizontal forces wouldn't be able to stop that. The idea is that friction is ultimately what a lot of people say it's the applied force that keeps it. It's not actually, it's the friction force that keeps it there. Now, to be reminded, so we'd have friction force. And in this case, because it's not moving, we'd call that a static friction force. And because it balances gravity, those two are equal in this case. Now, to be reminded about how this is going to work, friction and normal. So friction and normal forces, these are forces that occur at surfaces. Okay. So they are going to go hand in hand where one appears oftentimes another will appear. The idea here is that and you can imagine that if you release the applied force, then the friction force decreases. Eventually, this thing will fall. Gravity will take over. The real reason for that is that as you decrease the applied force, you are by consequence decreasing the normal force. And when the normal force decreases, the friction force decreases. So that is the main conceptual takeaway, that the friction force is proportional to the normal force. Okay. And the general way we write that, friction force, I'll generally do a lowercase f for that. We do this Greek symbol mu, looks like a U with a tail on both sides, and then that is multiplied by the normal force. Now, this we call the coefficient of friction. Now, you will have different coefficients of friction depending on whether it's static or kinetic. We'll get into that in a moment. But here's the idea. Like, I think the book has a pretty good demonstration of why this is the case, of why increasing the normal increases friction. So I'm just going to grab that and go paste this thing into our notes. Basically, the idea here is that what you have is you've got something that looks like this. And the idea is that the friction is a result from the fact that the surfaces aren't perfectly smooth. They're rough, and the edges will catch, and they'll catch from one another, and they'll resist motion is the idea. Now, when the normal force is small, you'll have some of the surface interacting, but large portions of it won't. When you start increasing the normal force and you cram these things closer together, you start getting more and more of the surface interacting, which is why you're going to increase the frictional force. Okay, so that is what is going on with that. That's why you're seeing increased frictional force as you increase the normal force. Now, again, you basically have two types of friction force. And we mentioned this briefly, but just want to go over that again. Two types of friction force. The first one is your static friction. Okay. And this is basically friction between stationary surfaces. Now, the key thing here is that the surfaces have to be stationary relative to one another. And basically, it just means that the surfaces are not sliding against one another. Okay. And then you have kinetic friction, and this is going to be friction between sliding surfaces. And both of these sliding surfaces, both of these frictional forces are going to follow a similar form as we just saw for the formulas. So the formula for kinetic friction, formulas or formulae, however you want to put it, the symbol we'll use will be F sub K, and this again will be kinetic. The subscript will indicate on the friction force indicates what type we're dealing with. For kinetic, it's simple. It's just it's always going to be equal to the coefficient of kinetic friction times the normal force. Now with static friction, it's a little bit different. What you have here is you have F sub S max. Okay. And that is equal to the coefficient of static friction times the normal force. Now, the reason why you have this F sub S max, basically, this is the maximum possible static friction. And the idea behind static friction is it's somewhat analogous to the normal force in that we saw that basically what the normal force does, it increases as much as it needs to in order to prevent two objects from accelerating through one another. And ultimately what can happen is eventually the normal force can break the objects, but well, that's kind of beyond the scope. The point is that because two objects can accelerate from through one another, the normal force will get as big as it needs to be. Static friction does something similar. Basically, static friction, F sub S, can be, I'll rephrase, is, I'll say, as large as it needs to be, but this is only up to F sub S max. It can't go any higher than F sub S max to prevent slipping of the surfaces. Okay, so the idea here is that if you have something just setting on on a rough surface on flat ground, there doesn't need to be any static friction. There could be, but there doesn't need to be in order to keep it from accelerating. Now, if you tilt that surface and the object doesn't accelerate, well, basically it's static friction holding it in place. Okay, and the static friction is only as big as it needs to be to keep the thing from sliding down. Now you keep on tilting it, keep on tilting it, keep on tilting it. Eventually, static friction needs to be too high, and it starts to slip. Now, when you tilt something on a ramp, you also, in fact, decrease its normal force. So that's another sort of interesting phenomenon with that. But the main idea is that with static friction, in general, you can only count from the normal, you can only get the maximum static friction. You can't calculate what the exact static friction is because it will be as large as it needs to be to prevent motion. Okay, so that's just something to keep in mind. Now, I'll show a couple of examples. These are just simple examples that involve a ramp. Okay, so example one, be like this: a box on a ramp starts to slip when the ramp is angled at 30 degrees. And then you might be asked to find mu sub s. Okay, this is the coefficient of static friction. Now, the fact that you're going to be dealing with static friction is kind of indicated in what they're telling you to find. But this thing right here, this starts to slip verbiage. Basically, what this is telling you, the starting to slip, if you see this phrase, it starts to slip. Basically, something starts to slip. Starts to slip right when F sub x max is exceeded. Okay, so when your coefficient of static friction would just start to exceed F sub x, that's when you say this thing starts to slip. So the condition we set there is F sub s is then equal to F sub s max, which means we set that formula mu sub s times the normal. Okay, so it's the starting to slip phrase that you should be looking for that tells you that you're dealing with F sub s max. Now, I'm going to draw both a picture and a free body diagram. So 30 degrees. We've got the box sitting on the ramp like so. Now we're not told what the box is. Maybe you're thinking, oh wait, mister, and we can't do this without the box. That's fine. We'll see in just a minute. But we know that the thing is just sitting there, so that's fine. Now I'm going to draw the free body diagram and over here, and we've got, I'll make these big. We've got our force of gravity. I'll do that. That'll be the plane. We said that that was 30 degrees. Well, we also know that we've got our normal force. Our normal force is perpendicular to the force of gravity. So that would be our normal. Or sorry, not to the force of gravity, to the surface. Perpendicular to the surface. I drew it correct. I said it incorrectly. And then lastly, we've got our force of static friction, which will be in the plane of the ramp. Now, the key here is that the static friction, there's a couple of keys. Well, the static friction and the normal are perpendicular, so we can definitely say that. Now, the main thing you want to make sure you do is you set up a rotated coordinate system. And I'll do these kind of axes in purple. We have the y-axis and the x-axis, okay? And the key here then is you want to set up your F sub x forces and your F sub y forces in those axes. Well, the positive ones are easy. We've got the static friction, which at this point, this is where I would define it. Since I know it's F sub s max, I would just define it as mu sub s times the normal force. And we have the normal force, which we don't know what that is yet. So we'll just leave that alone. And then in the other direction, we've got the components of gravity. Now, I did one similar to this last time, but I do really encourage you to know why this setup works, where basically what I'm doing is I'm breaking gravity into two components along the y-axis of my tilted coordinate system and parallel, at least to the x-axis of my tilted coordinate system. So that we get that kind of triangle right there. Now, this angle ends up being 60 degrees, which means this angle is 30 degrees. So as a reminder, when you set it up like this and given what they give you, your FG sub x ends up being FG cosine, or sorry, not cosine, it's sine, because the FG sub x is opposite. So FG sine theta, which just ends up being MG sine theta. Okay? And I'll put that, that I would also make that negative because it is going in the negative X direction, like it's going to the left. If we, if we tilt our head and we look, that looks like the negative X direction. The FG sub Y is also negative, but this is FG cosine theta, or negative MG sine theta. Now, I'm putting the negatives here because when we do the sum of the forces in the X direction and the sum of the forces in the Y direction, we want to have F and then minus FG sine theta for the X. So it's F sub S, and then normal minus FG cosine theta for the Y. Now we can replace these, so we get mu sub S minus mg sine theta. And then for the Y, I'll continue to divide that. We end up with n minus mg cosine theta. Now, last important thing to know, it's worth knowing that a sub x is equal to 0 because this thing is stationary. That's a sub x is going to be its acceleration along the plane of the ramp, and it's not moving in that plane. So it would just be stationary. It's a sub x is 0. A sub y for these ramp problems is almost always going to be 0 because it's not accelerating up or down perpendicular to the plane. That one is going to be one of the most common ways to set this up. So a sub y is equal to 0 as well. Now, given that's the case, we know that f sub x is then equal to 0 and f sub y is equal to 0. Remember, that's Newton's first law. If your acceleration in one direction is 0, then the sum of the forces in that direction is also equal to 0. Sorry, that should be f sub s. Should have been f sub s, and that was mu sub s times the normal. So if you caught that, good on you. Now what this means, we can solve this equation for mu sub s. That gives us mu sub s normal is equal to mg sine theta. This one gives us normal is equal to mg cosine theta. When we solve for mu sub s, we end up with mu sub s equals mg sine theta over normal. And then plugging in that normal there, we get mg sine theta over mg cosine theta. Those cancel. And we just end up with sine theta over cosine theta. That is that ends up being opposite over adjacent, which is just tan theta. So this is one way that mu sub s can be found in these ramp problems. Or in some cases, mu sub k. I'll do one quick example on mu sub k here in a second. But basically, that's what that does. So you didn't need to know the mass of the box. You just needed to because the masses ended up canceling. So you need to be able to do that algebra in order to clear that out. Now, I want to do another quick example, and you'll see that this is almost identical, and I just want you to see the similarity. So example 2, a box on a ramp slides down with constant velocity when the ramp is at 20 degrees. And I forgot, I didn't make an angle there, so it would actually be tangent of 30 degrees, which I believe is root 3 over 3, as I recall. But in any event, that's how you would find that. Now, a box on a ramp slides with a constant speed when the ramp is at 20 degrees. Now, before I ask the question or I give the instruction, I'd encourage you to try and do a free body diagram of this system. Do a picture, do a free body diagram, see if you get it right. It's worth checking to see how well you're grasping the free body diagrams, because that is really the essential skill at getting started in all of these. You got to be able to identify these forces accurately. So yeah, go ahead and pause and give that a shot. But what you would do, you'd typically be asked to something like this. What is mu sub k? Now, mu sub k, that indicates, that does give a little bit of it away. because that indicates that you're going to be dealing with kinetic friction, which is true because this thing is sliding now. So it's going to be a similar diagram as before. You're going to have mg, so the force of gravity on the box will be mg. Your normal will still be like so, and your friction will still be in the same direction. It's just kinetic friction now. Now I drew this angle way too big, but that's okay. We know I'll just leave it as theta, and we know that theta equals 20. That's fine. Now, again, it's worth setting up that it's worth knowing that when you set up these coordinate systems, this angle is also theta. It doesn't matter what theta is. But that's very helpful in setting up your diagrams. Now, give this one a shot, but hopefully you can kind of see. There's one other thing you need to know, and that is constant speed, which means that your acceleration equals 0. So a sub x is equal to 0 and a sub y is equal to 0 for our tilted axes. If it's going down at constant speed, it is moving along the x-axis. But in Newton's law, when we're dealing with Newton's laws, we don't really care that it's moving. We care whether or not it's accelerating. And constant speed means it's not accelerating. So acceleration is equal to 0. So from there, what we could then say is we can basically do exactly the same thing we did up here, and you end up getting exactly the same thing. Run through that again if you need to verify that. But it then just ends up just being mu sub k equals tan theta, which for our case would be tangent of 20 degrees. Okay, so that is how you would solve that one. So give that one a shot. One other thing I wanted to talk about is rolling objects. In particular, and this is true of all rolling objects, but one you're most familiar with is the force of a car. Now, we typically think of the engine as driving the car forward, and in a sense, that's right. But really, what the engine is doing, the engine is turning the wheels, and the wheels are exerting a force on the ground, and it's actually the force from the ground that's pushing the car forward. Now, if you think about what that force is, it's the frictional force. Frictional force. This is what pushes rolling objects forward. Okay, so that is basically what is going to be happening with these kinds of things. So if we think about an object that is rolling in that direction, basically, it depends. It does sort of depend what kind of how that's working. But basically what's going on is the net effect is that it's the frictional force that is pushing on the bottom of the wheel where it meets the surface. And so the question then is that static friction or kinetic friction? A lot of people will say static because it's moving, but kinetic because it's moving, but it's actually static friction. So static friction because the tire does not slip. Okay. So you have static friction there because the tire is not slipping when you are does not slip because the tire is not slipping when you're moving that thing forward. Now it's a little bit more complicated than that when you have a car because the friction force isn't quite doing exactly the things I said. This thing only works because of the friction force, but there's also a force from the car, which is or from the engine, which is turning the wheels, so that how that balance of forces that kind of affects whether or not the car speeds up, slows down, does all that kind of thing. We typically just view the force from a car as an applied force, but it is worth knowing that it is in fact the friction force that is responsible for moving the car forward. And this is why if you're on a frictionless surface or a low friction surface, You can hit the gas and your car won't go, but your wheels will spin. Okay, so you need that friction force to be able to be able to get the car to move. Okay, so that's worth keeping in mind. All right. The last thing I want to talk about today is drag. And this the drag force is worth checking out in some detail. And the reason I want to include it here is basically drag. Another way you can think about drag is it's friction between a fluid and a surface. Um, Air and gases in general are fluids. A lot of people don't think of them that way, but they are a type of fluid. They're what we call a compressible fluid. They behave in a lot of similar ways to other fluids. We'll talk about this a little bit later in the class. But they behave very similarly. And the point is that when they interact with surfaces of solid objects, they create some friction there. But it's a little bit different because that friction is not you can imagine that if you thought about that as friction, basically the normal force would be increased the faster this object was going, because basically the object has to push the fluid out of the way. Okay. And so drag ends up being, we can't model it as simply as just with a normal force. We end up modeling it with a number of different things. One of the more common models for drag, and the one given by your book, is this F sub D, force of drag. 1/2 times C, and then they do this thing look kind of like a P. It's actually a rho, AV squared. C is your drag coefficient, generally a property of the object and the shape of the object as such. Rho is the density of the fluid. So the idea here is that if you're traveling through a more dense fluid like water as instead of air, the drag will be greater. It's harder to push. Density of the fluid is kind of a way of quantifying the mass of a fluid. It takes more force to push a more massive fluid out of the way is the idea. And then A is the cross-sectional area of the object. So the way you can think about C is it's like a shape factor, but that shape factor can be weighted by having the object be bigger. And then V is the velocity square, or V squared, the V, that's the velocity. Now it's really this V that becomes a problem, because if we had the situation where only drag was acting, if only drag acts on an object, then basically what you have here is you would have something like this. So F sub D would be equal to ma if that was the only force, or the only one that was causing an acceleration, we might say. What you would have is you would have 1/2 C rho A V squared is equal to ma. And the idea here is that V would impact A. But we also know that acceleration then impacts velocity. So basically what you have is you have both sides of this equation determining the other one. So as one side changes, the other side changes, which in turn changes the first side, which changes the other side, and back and forth and back and forth. And really the only way you can do this, the only way you can analyze this, is with calculus. You need to start looking at very, very small time intervals and figuring out, okay, how exactly is this going to work? You can do it with analytical calculus methods or with numerical calculus methods, but either way, it's beyond the scope of what we're going to do here. So I wanted to indicate that. Now, there is one situation where we might use drag, and that is the situation of terminal velocity. And terminal velocity, basically, this is generally reserved for conditions of free fall. Free fall where maximum velocity is achieved. Now, in general, we don't think of free fall as there being is achieved. As there being a maximum velocity, at least if gravity is the only force acting on the object, gravity is just going to keep on accelerating the thing. There are relativistic limits, but that's way beyond the scope of what we're going to talk about. But the idea here is that gravity, gravity will just keep on accelerating the thing. And if there is no atmosphere, if there's no fluid for this object to move through, then that is true. Gravity will accelerate the thing. It'll just keep moving faster and faster and faster until something stops it, generally the surface of the planet. With terminal velocity, when you have an atmosphere fluid for an object to move through, that is not true. And basically, this is the condition where you have, if we were to draw the free body diagram, what you have is you have your force of gravity, and then you have your drag upward. And if maximum velocity is achieved, so V equals V max, this means something in particular. It means that acceleration is equal to 0. Okay, and if acceleration is equal to 0, then those two forces are equal, which means you can say that the force of drag is equal to the force of gravity. 1/2 C rho A V squared is equal to mg. Okay, so that's the condition of terminal velocity. The book has a couple of problems involving this, but the one I wanted to discuss real quickly is they give you for a skydiver, and they give you a bunch of the things. They say C is equal to 0.70. 2 zeros there. Actually, they only give one, but I'll guess. And then rho is equal to 1.21 kilograms per meter cubed. It's important to note that C is often a dimensionless quantity. They're determined largely, again, based on the shape of particular objects. But they tend to be determined experimentally, but they are dimensionless. They don't have units of their own. And then A, they say, is 0.18 meters squared. Now, this is interesting because it's cross-sectional area, so it's basically the area that's facing the direction of motion. So you can actually increase your cross-sectional area by, instead of going feet down or face down, by going body down. That will increase your cross-sectional area by quite a bit, which will also increase your drag. You can also do it by having those little suits that have like those little flying squirrel suits. I'm sure you've seen those, but those are basically, the idea is that one, they do change the drag coefficient, but additionally, they also really increase the cross-sectional area, which can basically make drag a much more impactful force. And then basically they say, okay, find V terminal. And basically, I should have indicated that it would be the terminal velocity right there if those two forces were equal. Solving for this algebraically, the terminal velocity is just 2 mg over the drag coefficient times the density times the area, all raised to the 1/2 power, or the square root. Now, given those numbers, they do the they calculate this out to 98 meters per second, which I believe is a little more than 200 miles an hour. So you're going quite fast, and that is still gonna, that's gonna be quite painful. The calculations of drag coefficients that's a big part of what the science of aerodynamics is doing. Okay. This is it, and it's very it can be very difficult, can be very precise. You can always refine these things. And so this is kind of what's going on now. Interesting little tidbit. One of the things that does impact drag coefficient, as it turns out, is it does tend to be I believe the mass can impact the drag coefficient. I would need to check on that to be certain, but generally less massive objects are going to have much smaller terminal velocities. Now, part of that you can see is that mass is just in the numerator, but I think that that decreasing the mass also increases the drag coefficient. So decreasing the mass, if that increases the denominator of this terminal velocity, that will make things quite that'll make your terminal velocity much slower. And this is why certain animals, their terminal velocity is basically harmless to them. The book talks about this. It says that a mouse, if dropped down a mine shaft, would walk away. A rat would die. A human would be broken, and a horse would be liquefied. Okay, so that's the idea that less massive objects can have the smaller terminal velocity, and they can withstand great falls much more readily. So worth knowing that, and hopefully this lecture was useful. Take a look at some of those at some of those friction problems that are given in the examples. I think those will be helpful. But I'm going to go ahead and end this lecture there. Thank you for joining me. I will see you next time.